Okay, good afternoon, or sorry, good morning, everyone. Hope everyone is doing okay. First of all, I really would like to thank the conference for inviting us and accepting the paper and taking us into consideration. My name is David Emmanuel Katz, and I'm representing the whole AI team at a company that I founded called Smart Layers, where we take care of automating the process of setting up complex ML models for document extraction for different business automation use cases. So a little bit about me. My background is in economics and business, but I've been developing software for the past 7 years, and we've been building Smart Layers for the past year. Today, I'm going to be presenting some of the core ML methods and methodologies that we use in Smart Layers, and we have applied this to a specific use case that we have studied, and I'll be talking more about today. The structure of my talk is going to be the following. First, I'm going to give an introduction about what we're going to study and talk, or what we have studied and we're going to talk about. I'm going to give an overview of the problem of information extraction in the context of our study. Then I'm going to give and explain an overview of our methodology. And finally, I'm going to present our results that we have published in our paper, finally drawing some conclusions based on these results. Structured information extraction is a technique that goes beyond simple OCR and assigns labels to every single token on a page. As we know, OCR has been a long-standing problem in computer science, one that has been pretty much solved by existing techniques. But OCR only takes businesses and users of analog to digital document processing projects the ability to convert documents into sequences of one-dimensional text, considering new line characters, spaces, tabs to be part of this one-dimensional sequence. At the end of the day, traditional OCR only gets us so far in being able to extract information from a document. Real-world business use cases depend on not only being able to digitalize their documents, but be able to plug into their automation, database, API systems that require fully structured data. Extracting a full string of text only from a document and trying to insert it to a structured SQL database model simply will not work. A great area of research in recent years has been to use advances in machine learning and statistical learning techniques to apply traditional classification and natural language processing to solve this problem of structured information extraction, where every single token of an OCR output or every single piece of text on a page can be either classified as a label that is not of interest or a label that is specifically interested and follows a structure and schema that we expect. Our research problem is narrowed down to a very specific context. We are interested in being able to build information extraction models for invoices with a set of additional constraints. First is that this set of invoices needs to be as small as and business applicably possible. What we mean by this is that we don't want to leverage hundreds of thousands of documents, as some published research that we have referenced does. The second problem that we want to clearly establish is that the invoices that we are going to be processing are going to be heterogeneous in nature. What does this mean? That there is no two invoices that are going to be potentially exactly the same, and we must assume that unobserved invoice structures will need to be predicted by our model. Specifically, what we intend to do is extract tokens from a document, understand where they are in the document, assign them a label, an OCR label that we call in our use case, but this is just the problem of a single class token or a single class classification problem in machine learning applied to tokens on a document. And the subset of entities, target entities that we would like to extract from the document can be seen in the bottom right-hand table. We are interested in only a subset of these target entities since they are the most applicable to a business process outsourcing or automation use case. Again, our constraints are that we cannot follow or assume that our document has any sort of template or that has any sort of understanding predetermined nature that we can leverage. We also would like the data set to be as small as possible and understand what we could do for a real world application use case. In this context, a small data set will consist of 200 documents, each of them spanning multiple pages, and every document on average will have a number of tokens that at an aggregate would give us more or less 400,000 tokens. I would like to highlight some differences with traditional natural language processing techniques. In document understanding, human readable documents, the layout and the two-dimensional structure and the relationship to where different tokens are on a page have a high amount of information. And this information is what this information gain that we achieve from understanding and using the 2D layout of tokens is another purpose of this paper. The problem with one-dimensional traditional natural language processing techniques is that they can easily lose the overall structure of a document. Natural language processing advances in the last decade have been highly focused on what we know as large language models that focus primarily on paragraph-based text or sentence-based text, where it doesn't matter where this text is in the document. The only thing that is of interest is the one-dimensional sequence. As previously mentioned, the issue with traditional OCR is that once we observe a specific document that we need to digitalize, that can either be a scan or some sort of PDF that does not contain any character information, but just contains the image render of this document, passing it to traditional OCR software will give us a one-dimensional sequence of text, including new lines. These new lines creating this system of separating and the apparency of different two-dimensional structure, but at the end of the day, it's just a one-dimensional structure that lacks any understanding of surrounding tokens with respect to token. Even recent advances in the large language models that use things such as multi-headed attention or attention components within their model know how to pay attention, but in respect to a one-dimensional sequence. Again, it will not consider tokens that surround a token from a document. Document automation with structured information extraction allows for every single piece of a document to be identified as relevant, containing specific token, or can be labeled as undefined. This allows us to plug and play with existing architectures that companies are already using and not have to create this additional problem of having this, semi-structured data that is converted to another semi-structured data format. Again, we have observed, especially in the last decade, large improvements in natural language processing and the creation of extremely large language models that closer and closer appear to be able to understand many of the intricacies of our language. We do, as researchers and professionals that dedicate ourselves to the extraction of information and document automation, we would like to somehow leverage the advances in these models, but they are not directly applicable because of the one-dimensional nature that they assume. Additional specific challenges applying information extraction to the real world is that the OCR is an overall error-prone process. It's an analog to digital conversion, considering that we have some sort of analog image of a document and we need to convert it into a digital format, and any analog to digital conversion is going to be error prone. Documents don't have the luxury of having error bit checking. So what you see is what you get and what we can process will have errors. Many existing papers on the subject of information extraction do not necessarily take into consideration the errors of OCR, and many of the papers that we reference contain scores for the classification of these tokens. What we have realized is, especially for a use case in finance where we're processing invoices, is it's not enough to only look at the accuracy of the classification of tokens, because at the end of the day, if there's an issue with the OCR, or if there's an issue with how your OCR distributes tokens and how you label tokens, and furthermore, how you merge these tokens together, can have a large impact on the output of our model. We wanted to introduce a new type of metric that will allow us to score the impact of these errors and the joining and the characteristics that can create errors in the OCR process that digitalizes our analog document. So before I explain our specific methodology, I just want to go over some formulas. As we might all know, precision and recall, these are accuracy metrics specifically. These are evaluation metrics for classification problems, where precision measures, our true positives over our predictive positives. Recall, we're talking about the true positives over the positives in our data set. Our accuracy is just the sum of the true positives and the true negatives divided by the total data set. And our F1 score is a harmonic mean of the precision and recall. Traditionally, document understanding and key information extraction papers have been highly focused on reporting F1. What we start to introduce in our paper and we start to consider is a metric known as the Liebenstein Ratio. And the Liebenstein Ratio, to understand it, we must understand the Liebenstein distance. And this is just the count of the inserts, deletes, and replacements that a string needs to match another string. It's going to be an integer value. And the Liebenstein Ratio is going to be the Liebenstein distance between a prediction and a ground truth divided by the length of the ground truth. In our research, we have observed that there are different variants that we can apply to this Liebenstein ratio, such as summing the length of the ground truth plus the length of the prediction. But at the end of the day, all of the Liebenstein ratios that you will be able to construct are going to be highly correlated. And at the end of the day, if we see high levels of Liebenstein ratio and high levels of F1 scores, we can conclude in general with high levels of probability that we will be able to extract information in a document from a document in an extremely precise way. Not only because we are classifying the tokens correctly, but we are also merging the tokens correctly. This merging of tokens can have a very large, the method we use to merge tokens can have a very large sensitive impact on the Liebenstein ratio, and hence the applicability of a document extraction model to the real world. Also, to understand our method, I would like to simply recall or introduce the GraphSAGE, or the graph sample and aggregate model that was presented by Hamilton, Ying, and Leskovec in 2017. And this is a relatively novel method in machine learning and specifically deep neural networks that allow for the representation of a node in a graph without having to know the fixed structure of a graph beforehand. Inductive representation is the idea of being able to represent a node in a graph using some sort of embedding, where we do not have to know, or we do not have to traverse the entire graph if we don't have to. Previous methods in graph neural networks assumed some sort of fixed size of the graph, and therefore they were only transductive. And a transductive graph neural network is a graph neural network that needs to know the size or the shape of the graph beforehand. Due to our constraint of having to process invoices in different formats and in different shapes that can have small or large differences in the overall format in which the data is presented, we needed to use some sort of a method that, if we were to apply, as we will soon see, the graph neural network approach, we definitely needed an inductive approach. The next piece of existing technology that we use for our methodology is the universal sentence encoding model presented by Google and engineers and researchers from teams at Google. And this was presented not too far back. It's a little bit more recent than GraphSAGE, but from more or less the same period. And what USUM allows us to do, it allows us to have a dense representation of text in different sizes. So we can have independent pieces of text that are represented in a dense vector. And these dense vectors leverage large models such as BERT and Albert and these very large language models that have been trained on terabytes and terabytes of text that are ever so close to understanding the intricacies of human language. By using, as we will soon see, the universal sentence encoding model is a core piece of our methodology. Okay, so now I would like to present the natural language processing plus graph neural network approach that we present in our paper. And what we do is we also measure our model against naive models that don't consider graph structure to measure any information gain, but only use the NLP. So an overview of how our model works is the following. First, we will be able to, in a training scenario, what we have is we have a data set where every single token in this data set will belong to a document. A document will contain many tokens, and a token is just a sequence of characters that have been outputted by an OCR. Different OCR engines have different ways that they will output tokens. So what we wanted to make sure is that we were able to have an approach that will be independent of the OCR engine. So we assume that these tokens are distributed within documents, and all of these documents exist in our data set. Every single token will either be annotated as corresponding to a target entity of interest, or it will be labeled as undefined. What we first do is we get every single word in a document, along with every single line that that word shares, and we pass this information into three separate processes. The first process is we will pass it into a trained GraphSAGE model that has been currently trained on all of the word tokens and their positions. This GraphSAGE model will be explained in the next slide, but just know that what the trained GraphSAGE allows us to do is allows us to pass the position of a token and all of the tokens that surround it, so the graph that represents the document, and will give us a vector embedding of this token. And this vector embedding represents information about the token, but also its neighboring tokens. The universal sentence encoding model is used directly to vectorize every single word token along with their line tokens. Now, once we have passed the green phase, we enter to the phase where we can use more traditional neural network techniques in which we merge all of our vectors into a single feature matrix. And we also extract the labels from all of the word tokens in order to be able to pass them to a simple feed-forward vanilla neural network that is trained to classify the vector and hence classify the word token, the position. The output of the neural network will assign labels to every single token in our document. And these labels are not necessarily joined in the way that a human will expect it to be joined. It could, all of the tokens are individually predicted individually, or it could also be that many words are divided up into n tokens arbitrarily. So what we do is we apply a completely deterministic process where we merge the tokens. The specifics of our word token merger could be read in our paper, but on a high level, what we do is we check if tokens are close to each other laterally, and if they're very close to each other based on some metric D, what we end up doing is we join these tokens. Further research outside the scope of this paper has shown that we can develop different methods for merging these tokens that will have impact on different types of documents. But for the invoice problem, we were only interested about mostly understanding what this trained GraphSAGE adds to the picture outside of just classifying the word tokens. Now, just a brief explanation again of this Liebenstein ratio. The Liebenstein ratio is the Liebenstein distance divided the length of the ground truth. So we have some tokens on the right-hand corner that we can show what the output of a specific OCR model could be at the top and the ground truth at the bottom. And here we can see that because there are 9 characters, we're going to have 1 error. And what we have to do is we have to, calculate the Liebenstein distance and divide it by the length of the ground truth, right? And we get a score of 0.88. Now, it is very common, as mentioned, that the impact of these errors will affect the end process of several real-world applications. And a common feature that is done in current academia is to just completely ignore OCR mismatches and errors related to OCRs. But what we would like to do is we would like to embrace it and calculate the score on top of our F1 scores to understand how really applicable our models are to real-world business processes. Explaining a little bit more in detail about how we create this trained GraphSAGE model. So as mentioned, GraphSAGE is an algorithm that allows for the representation of nodes in a graph using learning techniques, as in that the different parameters that are learned by the GraphSAGE allow for a better representation of these nodes in a latent space. To create this trained GraphSAGE model, what we do is we take the individual tokens that correspond to a single graph, and a single graph being a single document or a multi-page document, and we pass all of these tokens into a GraphSAGE algorithm that allows us to output a trained GraphSAGE algorithm. To be more precise, as many neural networks work, GraphSAGE is initiated with random weights and traverses the graph in a certain way that allows for the updating of parameters that are optimized via traditional gradient descent methods. Now, it's very important that GraphSAGE does not actually know the labels that we would like to assign to the tokens, because in a real world use case, when we have to run a new unobserved document on GraphSAGE or through our pipeline, we won't know the label. But what we will know is different Boolean statistics that we have calculated, Boolean features that we have calculated that correspond to every single word. And these are, we consider them just functions that are applied on the word vector that allow for adding additional attributes to the nodes. GraphSAGE is a very powerful algorithm, and it allows for every single node to contain as much arbitrary information as a user will like. Obviously, this information needs to be completely ready and set up for machine learning, so we can't just pass it text. What we need to do is we need to process, so somehow every single node is represented by a vector. By traversing our graph until we reach a specific point in minimizing our loss function, our trained GraphSAGE is now able to represent tokens and represent different neighbors of those tokens and how those neighbors are related to the token itself. So I wanted to illustrate a little bit better the example and the layout of a document graph structure and what we talk about when we're saying a document graph. What we do is we take the distances between every single token and connect them using a specific weight. And all of these weights that connect all these tokens are our graph representation of the document. Every single node in this graph is represented by a different vector. And as well, we have the different prediction labels associated to them, knowing if they're either a token of interest or if they are just a undefined token that we must not worry about. As You may observe many of the use cases that can be applied, and specifically the one for invoices, are going to include high levels of imbalance, in that most of the tokens on this page are not going to be of interest to us. Therefore, we need to make sure that we're using loss functions that account for the high levels of imbalance in our data. Now I'm going to talk a little bit about our experimental protocol and finally show you our results. We sourced 205 multi-page PDF invoices ranging from 1 to 3 pages, most of them containing only 1 or 2 pages. And they were sourced from a real-world business process outsourcing company that takes care of the processing and data entry of these invoices. So we were sure that these were invoices that were directly applicable to industry, and that were, if we were able to extract them with the degrees of error that are satisfiable for our business use case, then we would know that we have correctly been able to create a model that will be able to be used in the real world. Our test train split was a 70-30%, and our invoices contained contained documents in 3 different languages: Spanish, French, and English, proportionally distributed within the 205 invoices. An additional detail about the universal sentence encoder model that is used to create a dense representation of the line, but as well as the single token, is that it supports multiple languages. The OCR engine that we used in this experiment was the Tesseract version 5, an open source OCR engine created by Google. The results that we were able to obtain were of satisfiable to a certain point, and there's definitely a starting point with room for improvement. However, we would like to observe that our results are, in the classification aspect, very, very high, with F scores on average of 95 and above. Next, an analysis of the Liebenstein ratio shows us that some information is extracted with high degrees of accuracy and certainty, but some of them contain problematic issues that can be related to either the misclassification of some tokens that should be part of the final target entity that needs to be extracted, or other non-trivial interactions between the prediction of tokens and the merging of the boxes. As we can observe, our worst field was the tax percentage, and we understand that this has to do mostly with the confusion of number and percent signs when extracting this target entity. Also in our paper, what we would like to do is we would like to understand the information gain that is observed by including the graph structure of our specific method, and including the graph structure of a document, and how including the embedding of surrounding tokens to a specific token will impact directly or indirectly the output of the classification and the task of information extraction. And what we did is we just used simple classification methods, linear, and just a very simple deep neural network that were only used and trained on the word vectors and their positions, without taking into consideration the additional G feature that we mentioned earlier, that was the output of representing a node through our trained GraphSAGE model. And what we can observe are very, very poor results, therefore indicating that there is a high probability that the graph structure that we used in our model allows us to extract information with higher degrees of accuracy. I would like to discuss our conclusions. The first one, as mentioned, is that graph embeddings introduce high predictive power. And this is natural and can have a more theoretical explanation, in the sense that the two-dimensional layout of documents is exploited in a more precise way by embedding every single token using the GraphSAGE algorithm. We also observe in our paper that the results are extremely sensitive to the token merging strategies. Different strategies can impact the results of merging tokens, even and pretty unusable and poor real world results, even if you have F scores of 99%. Another specific conclusion is that the GraphSAGE algorithm allows for a hyperparameter that has to do with how many layers it will jump to a different token, what is the distance of the maximum sampling of the surrounding tokens. And what we have observed is that sampling beyond n equals 3 holds no predictive value. And finally, what we were able to observe is that on some fields, but specifically the fields that have over 90% Liebenstein ratio, can achieve achievable results with a real world use case on only about 200 documents. Thank you everyone for allowing me to present my paper, and this is the end of my presentation.